And finally, the reaction mechanism. So we've seen the reactants, we've seen the products, but what actually goes down on the in-between? Well, I got some bad news. Most reactions do not happen in one single step. This is actually pretty obvious. You take a look at the reaction like the one we have here. So here's the players in this reaction. We have two NOs, so those would be represented right here with a nitrogen bonded to oxygen, nitrogen bonded to oxygen. We've got two of them, so they're separate from each other, reacting with an oxygen here. And what they're forming is two nitrous oxides, which are these guys right here. And so these two ingredients would react to form those two products. And if we look at this right here, in order for these two to form, you would need each of these nitrous oxides to gain one oxygen. So in order for that to happen, remember collision theory, in order for reactions to occur, things have to hit each other. And so this right here, nitrogen, would have to slam into that oxygen at the exact same moment that this nitrogen right here slammed into that oxygen. Because if just one nitrogen bumps into one of those oxygens, this oxygen is not going to break its bond with that oxygen just to join this guy and leave that guy packing. It would have to happen at the exact same time. So these two bonds would have to form at the exact same moment. The odds of that actually happening are extremely low. The odds of those two nitrogens hitting that one oxygen molecule with the right orientation, the right amount of energy, and forming those bonds, it's not going to happen. So that tells us something must be happening in between this point right here and this point. Okay, so let's look back at this main page. We can see right here that scientists have proposed a reaction mechanism. So what actually happens? We see here that the two NOs actually bond with each other to form N2O2. And then that N2O2 reacts with oxygen. Now, what makes this work is the fact that since we have those two N2O2s stuck together, they can react with one oxygen. So you're not counting on two separate NOs coming and hitting an oxygen. It's just one molecule hitting another molecule and forming that right there. Now, sticking with the idea that things can cancel out, that N2O2 is created, then destroyed, and so therefore overall it doesn't really exist. And so in the end, our overall reaction is going to be this guy right here, which matches up with the reaction that we would put on a piece of paper. And so what we can see right here is reactions do not occur as single steps. More often than not, they occur as multiple steps, yielding a final product like this. Okay, let's get some terminology out of our way real quick. Looking with this reaction we just looked at, that N2O2 that's created, then destroyed, or produced and then consumed, so that overall it does not exist in the reaction, is called an intermediate. So a product or a chemical molecule that's created, then destroyed, doesn't exist in the end, would be called an intermediate. Generally, these are really unstable. That's what makes them react or decompose into our final products. So just a refresher, the rate law for an overall reaction can only be found experimentally. So let's take, for example, nitrous oxide reacting with carbon monoxide to form nitrogen monoxide and carbon dioxide. The rate law for this particular reaction would be second order with respect to NO2 and zero order with respect to carbon monoxide. Another way of saying that, instead of putting that zero order in there, is the rate would be equal to the rate constant times the concentration of NO2 squared. But when we look at elementary steps, we can predict the rate law for elementary steps. Since we're taking an overall reaction and breaking it apart into chunks, we can actually look at the balancing coefficients and use those in our rate law. And so this particular reaction occurs in two steps. The first step would be that one right there. Second step would be that one right there. So the rate law for this very first elementary step would be rate equals K1, that's the constant for step 1, times the concentration of NO2 squared. How do we know it's squared? Because of that 2 right there. But Mr. Jones, you said you couldn't use those to figure out the order. Not in the overall reaction. However, on the elementary steps, those in-between steps that happen in the reaction, you can use the balancing coefficients to tell you the order. So then the second step of this reaction, which has nitrogen trioxide reacting with carbon monoxide to form our products, we can see that the rate would be equal to K2, since it's step 2, times the concentration of NO3, since there's one of them, and 1 carbon monoxide. So it would be first order with respect to both of those. Now, if we consider the relative speed of both of these reactions, this reaction right here is extremely slow. This one, though, is very, very fast. And so that NO3 is produced slowly by this reaction, but as soon as it's produced, it's consumed almost instantly by this reaction since it's faster. Since this one right here is the slowest step, that means it is what we call the rate determining step. That means the overall speed of this entire reaction is determined by this one right here. Why is it determined by that one? Let's say you're running in a race and there's only one lane, so you're stuck behind someone who's running really, really slow. Even if you're a really, really fast runner, you can't go any faster than that person in front of you is going. That's just like this. So this is an extremely slow reaction. So this one, even though it might be fast, it can only go as fast as that one is going to produce NO3s. And so what can I do to speed up that first reaction? Well, I can add more NO2s. If I increase the concentration of NO2, I'm going to increase the rate at which those are produced. What if I increase the concentration of, say, carbon monoxide, that guy right there? That's not going to increase the speed of the reaction because this reaction is limited by this one. And so if I increase CO, it doesn't matter because if this one's not producing enough NO3s, we can have a billion COs and it's not going to make any difference. So if the only thing that affects the rate is the concentration of NO2, and it has a doubling effect since there's two of them, that means that it's second order with respect to NO2. The other reactant, which was carbon monoxide in the overall reaction right there, since increasing the concentration of that guy, which is in the second step, has no effect on it, it would be zero order with respect to CO. That's why the rate law for this reaction overall would be equal to rate constant, concentration of NO2 squared, and since CO is 0, you wouldn't even put it in there. So we can determine a rate law based upon experimental data, but we can also find it using elementary steps. So when a mechanism has a slow initial step, so a slow step 1, the rate law for the overall reaction is equal to the rate law for that step. And that's why the rate law right here, that one, is the one that determines the overall rate law. All right, let's change things up a little bit. So we're going to deal with the same reaction. We're just going to change the speeds just for fun. So let's say that this first reaction, so step number 1, is a very, very fast reaction. What will happen here then is this reaction is going to pump out a buttload of NO3s. As a result, as that concentration of NO3s builds up, they're going to eventually start decomposing back into O2s and NOs. So we'll set up an equilibrium. And the second step would be our slow step then. And so according to the slow step then, that would be our rate law. Rate would equal K times the concentration of NO3 times the concentration of NO. The problem is NO3 is not part of our overall reaction. And so we're not going to be able to use this as our overall rate law because we can't change the concentration of NO3. We can only change the concentration of NO and O2. So we're going to have to modify the rate law and just do some algebraic solving there. So the rate in the forward direction for this step is going to be the concentration of NO times the concentration of O2, 1 to 1. The rate in the reverse direction would be the inverse of K times the concentration of NO3, and so that would be the rate that it's going to go backwards. So those two K values are going to be the same magnitude. This one's just the inverse of that one right there. So in other words, if this number is 4, that would be 1 over 4. And so then those two values would be equal to each other. We've got our rate constant times the concentration of NO times O2 would be equal to the inverse of the rate constant times the concentration of NO3. Now if we rearrange this, we can solve it to say that NO3 is equal to K1 divided by K inverse times the concentration of NO to O2. What this is going to let us do is plug that in for where it should be, which would be down here. So the rate for this step, which is the rate determining step, since it's the slow one, would be equal to the K times NO3. We can't have the NO3 in there because it's not part of the overall reaction. So we're going to swap that NO3 right there out for this value. And when we do that, when we plug that in, we can go ahead and cancel a couple things out, and combine like terms, and so what we're going to end up doing is we will take those K values, multiply them, and divide them, and get a third K. And then when we multiply the NOs in, we would get, of course, NO squared because of those guys right there, which means it would be second order with respect to NO times the concentration of oxygen. So it's first order with respect to oxygen. Okay, let's simplify this though, just for future, so we don't have to go through this entire process. If we're going for this as our overall reaction, we determine the rate law from the slowest step. Step number 2 is our slowest step, which means that right there is our rate law. However, we can't write a rate law for an overall reaction with a reactant that's not actually in there. So NO3 we got to get rid of. The concentration of NO3 is dependent upon 1 oxygen and 1 NO. That means we can swap that guy out for the concentration of O2 and the concentration of NO. And so that means the rate is going to be dependent upon 1 nitrogen oxide there, 1 nitrogen oxide there, so that'd be NO2, or NO to the second order, and then a single oxygen from that guy right there. And so then our overall rate law becomes rate equals K, or a rate constant, times NO squared times the concentration of O. Okay, so determining the rate law, chemists usually determine the rate law through experimentation. They use the rate law to figure out what the elementary steps are. And so in actual scientific practice, they don't sit down with a set of elementary steps and then figure out the rate law. They would figure out the rate law from experimental data, just like we've been doing, and they would use that experimental data then to determine what the intermediates are, what the steps are going to be. Because thinking about it, if you've got something that's 0 order with respect to a particular reactant, that's going to tell the scientists, all right, in one of the steps, that's not going to be there, and that's going to be the slow step.